In Module 6, Lesson 4, we're going to move on to creating histograms from our frequency tables. The boys and girls basketball team at Roosevelt Middle School wanted to raise money to help buy new uniforms, and they decided to sell hats with the school logo on the front to family members and other interested fans. To obtain the correct hat size, the students had to measure the head circumference, which is the distance around the head of the adults who wanted to order a hat. The following data represents the head circumferences in millimeters of the adults. Hats come in 6 sizes, extra small through double X, or extra extra large. Each hat size covers a span of head circumferences. So the hat manufacturer gave the students the table below that shows the interval of head circumferences for each hat size. The interval 510 up to any values less than 530 represents a head circumference from 510 to 530, but not including 530. And we complete the tally, or the frequency table, with the data listed in our list above. There's 513 and 525. Then 531, that would be a small. 533, 535, 535, 542, 543, 546, 549. Then 551, notice the data is in order from least to greatest, so that helps. 551, 552, 552, 553, 554, and so on. And our completed frequency table then shows 2 extra small, 8 small, 15 medium, 9 large, 4 extra large, and 2 double X. If someone has a head circumference of 570, they would need a hat size of a large. We completed our table up above. The hat size of the center is clearly medium. We have quite a few mediums. And what we should notice is the data starts small and increases greatly at medium and then decreases as the sizes get larger. One student looked at the tally column and said that it looked somewhat like a bar graph turned on its side. A histogram is a graph that is like a bar graph, except that the horizontal axis is a number line that is marked off in equal intervals. To make a histogram, we'll draw a horizontal line and mark the intervals. Then we'll draw a vertical line and label it frequency. Then we're going to mark the frequency axis with a scale that starts at 0 and goes up to something that is greater than the largest frequency in the frequency table. For each interval, we'll draw a bar over that interval that has a height equal to the frequency for that interval. For example, notice that the axes, of course, are both at 0. Then you should notice this rather diagonal Z. This is what we call a break, and it is indicating that we are skipping from 0 to 510. That's just so that we don't waste a whole lot of space in all of those sizes that are not on this chart. And we can do that on this x-axis. Where we can't do it is on the y-axis, because that will change the shape of the data. But notice the y-axis then is marked off into intervals of 2, because we need to go up to 16 since we have a 15 in our data set. You can count by different numbers. You could count by 5s, by 10s, by 20s, by 100s. So the frequency axis can represent a great number of different sizes, or a great number of data. So our histogram shows us graphically that the center of our data is clearly 550 to 570. And if we were to add two more measurements of 551 and 569, both of those would also fall in the center, and that would increase our table by making this center bar 2 more units high. Because the 40 head circumference values were given, we could have constructed a dot plot to display the head circumference data. What information was lost when the histogram is used to represent the data distribution instead of a dot plot? Well, looking at our histogram, you'll notice that we don't have the individual sizes. We just have the ranges of the sizes. So we don't know the exact head circumferences in the histogram. Suppose, though, that there had been 200 head circumference measurements in the data set. Why might we prefer to summarize this data using a histogram rather than a dot plot? A dot plot with 200 values would require us to have 200 dots on it, and could be quite a large dot plot. On the other hand, we can display 200 values on a histogram even in the same amount of space that we have represented the 20 or the 40 head circumferences we have here, because our frequency axis could change. Instead of intervals of 2, we could make it intervals of 5 or 10 or even 100 if necessary. So we can display a large amount of data without creating an extremely large display using a histogram. A dot plot requires 1 dot for each piece of data and would be very large to accommodate 200 pieces of data. A histogram is useful to describe the shape of the data distribution. It is important to think about the shape of a data distribution because depending on the shape, there are different ways to describe important features of the distribution, such as center and variability. A group of students wanted to find out how long a certain brand of AA batteries lasted. The histogram below shows the data distribution for how long, in hours, that some AA batteries lasted. Looking at the shape of the histogram, notice how the data mounds up around a center of approximately 105. We would describe this shape as mound-shaped or symmetric. If we were to draw a line down the center, notice how each side of the histogram is approximately the same or mirror images of each other. This means the graph is approximately symmetrical. Another group of students wanted to investigate the maximum drop length for roller coasters. The histogram below shows the maximum drop in feet of a selected group of roller coasters. This histogram has a skewed shape. Most of the data are in the intervals from 50 to 170, but there are 2 values that are unusual or not typical when compared to the rest of the data. These values are much higher than most of the data. We would say that this is skewed right because we have these unusually large data values that are to the right of most of the data. So in looking at 2 different skews, please notice that the graph on the left is skewed left because there would be data that is much further to the left than the majority of our data. And the graph to the right is skewed right because, again, there are values that are much further right than most of the data. So when we are talking about a skew, the skew is in relationship to the values that are out of the way or further away from center. So now in practicing, our first histogram shows the highway miles per gallon of different compact cars. If we're going to describe the shape of this histogram as approximately symmetric, skewed left, or skewed right, we want to see if there is some center that would show relatively equal parts. But if we split it down the center, they're not relatively equal. What we see then is that there is some data that's hanging out further to the right, which makes it skewed right. If we were to draw a vertical line on the histogram to show where the typical number of miles per gallon for a compact car would be, we would put it right about here. And the shape of the histogram then tells us that most cars get around 31 to 40 miles per gallon. But there is one car that gets between 49 and 52 miles per gallon. If we describe the shape of the head circumference histogram that we had in exercise 5, we would say that that is approximately symmetric. No, nothing sticks out one way or the other. Another student decided to organize the head circumference data by changing the width of each interval to be 10 instead of 20. So this is the histogram that that student made. Please notice our intervals now are not from 510 to 530. They're from 510 to 520, 520 to 530. So each of these intervals are smaller, and the data then would have to be reorganized in the frequency table to represent the smaller data intervals. And this histogram, in comparison to our original histogram, seems to be symmetrical. Maybe not quite as symmetrical as the other, but it does have generally the same shape and center. Spread out more, of course, and so when it's spread out a little bit more, it doesn't look quite as symmetrical. This new histogram, again, appears relatively symmetrical. And head circumferences from 570 to 590 would be 4 plus another 5. That would be a total of 9. And 571 would be included in the interval from 570 to 580. 610 would be found in the interval from 610 to 620, because when we think back to our original histogram, our starting number was included in the interval, but our ending number was not. So 610 would be included in the next interval, since 600 up to but not including 610 would be the interval before it. 571 is in 570 to 580, and 610 is in 610 to 620. Remember, a histogram is a graph that represents the number of data values falling in an interval with a bar. The horizontal axis, side to side, shows the intervals, and the vertical axis shows the frequencies, how many data values are in the interval. Each interval should be the same width, and the bars should touch each other.